Hi, welcome back. In this video, we're going to get a little introduction to related rates problems and outline the steps for solving these problems. In any related rates problem, there's always a goal. The goal is always to compute some rate of change of some quantity using a rate of change that's given to you of some other quantity. The hardest part is finding the equation that relates the two rates of change. We're given one rate of change, we want to find another rate of change, so we have to find the relationship. And in mathematics, a relationship is an equation. So the hardest part is coming up with the equation that relates the two rates of change. So what we're going to do is start with the relationship between the quantities. The quantities that are changing are all functions of time, right? They're changing as functions of time. And so their rates are derivatives with respect to time. So what we're going to do is start with an equation relating the quantities, and then we're going to differentiate those things to get another equation relating their rates of change. So let's look at a quick example. So this is similar to the basketball inflation example that you've already seen. Suppose we have a cube and we're pumping air into the cube and the cube is expanding. So suppose the air is being pumped in at a constant rate of 144 cubic centimeters per second. Now, as you can imagine, the length of the side, all the sides are the same length, those are all getting longer. The sides are all getting longer. Now, those aren't lengthening at a constant rate. They're actually, the rate of change of the side of the cube is actually also a function of time. It's not going to be constant. But suppose we're asked how fast is the side of this cube changing at the moment when it's exactly 2 centimeters long. Okay, so the rate of change is actually changing, but we want the rate of change at the moment when the length of the side is 2. All right, so in every related rates problem, you're always given a rate and then asked to find another rate. So the best thing to do is write down exactly what you're given and exactly what you're asked to find, and to write those as derivatives. So in this problem, the rate that we're given is the derivative with respect to time of the volume. So I'm going to write it as dV dt, and it was given as 144 cubic centimeters per second. The rate that we're asked to find is the derivative with respect to t of that side, s. So it's ds dt that we're looking for when s is equal to 2. All right, so once you write down the two rates, the one that you're given and the one that you're asked to find, you look at the two quantities that are changing. In this example, v and s are the two quantities. And so now our goal is to come up with an equation involving those two variables, just v and s. So in many of these problems, it's a simple geometric formula. So in this problem, it's just the volume formula for the volume of a cube. V equals s cubed. All right, so we have the relationship between v and s. Now we need a relationship between dV dt and ds dt, so we just differentiate both sides. So on the left, I'm differentiating with respect to time, and on the right, I'm differentiating with respect to time. Notice on the left, I just get dV dt. On the right, notice that s is a function of t, but we also have s to the third, so we have a function of s. We have a composite, basically. So we're using the chain rule on the right side. And notice we don't see any t, right? But we know it's an implicit function of t. So we're going to use implicit differentiation, or the chain rule. on the right side. So we bring down the 3, reduce the exponent by 1. That's the derivative of the outside with respect to the inside. Then we multiply by the derivative of the inside. So the derivative of the inside is ds dt. So remember, we're looking for ds dt when s is equal to 2. So if I want to solve that equation for ds dt, I just divide both sides by 3s squared. I get ds dt is 1 over 3s squared times dv dt. And now I can start plugging in. So ds dt evaluated at s equals 2 is 1 over 3 times 2 squared times 144. And I get 12 centimeters per second. All right, so that's a brief example, a relatively simple one. We're going to do a few more, at least 3 more videos after this, but I want to outline the steps. So the steps in any related rates problem look like this. It's a word problem, so always the first step is to read and understand the problem. Usually you read it a couple times, you may not totally understand it until you do steps 2 and 3. So step 2 is draw a picture, if possible. In many of these problems there's something geometric going on and you need to draw a picture. And then step 3 says assign variables to quantities that are changing and then label the drawing with those variables. And then after you set up all your equations and you differentiate, that's when you'll be plugging in numbers. And we'll do some examples in the next couple of videos to make it clear what that means. Step 4, state what's given, state what you're asked to find in terms of derivatives. So don't just write find how fast the side is changing when it's 2 centimeters long. No, we already know that. Put it in mathematical language. And step 5 is write an equation that relates the quantities that are changing. So you're going to write down in step 4 2 rates of change, for example dv dt and ds dt. And so the quantities that are changing are v and s. So in step 5 you need a relationship between v and s. So you need an equation with just v and s in it. Then step 6 says differentiate both sides with respect to time, and that's where you get the relationship between dv dt and ds dt, or between the 2 rates, the one you're given and the one you're asked to find. And then finally step 7, plug in everything you're given and solve for the rate that you were looking for. We're going to go through a few more videos. We'll do some pump some water into a conical tank, we'll pull a boat into a dock, and we'll fly a kite. All right, I'll see you there.